Right, so that all good on your end?
Yes, we can see it. Thanks, Dylan.
Cool. Right, so yeah, thanks thanks for having me first and foremost, and thanks to Ro, Michael, and Kate, and the others behind the scenes for putting the event together. My name is Dylan McCarthy. I'm currently working with Arup as a geospatial consultant, and last year I was studying geospatial data analysis at UCD. The presentation here will be going through some of my research from last year. So my thesis looked at automating shoreline delineation and applying this methodology to calculating both long-term and short-term shoreline evolution in County Wexford using satellite imagery from the Landsat and Sentinel catalogues of satellite images. So for starters, just to outline the global scope of the issue, the issue of shoreline evolution is important due to the number of people and environments affected by the changing position of the shoreline. In 2007, for example, the OECD projected current populations and assets exposed to the hazards associated with sea level rise and flooding, as well as anticipated future populations and assets at risk. And the tables here show populations and assets at risk. And you might notice a trend where developing countries tend to have more significant populations at risk compared to the developed countries appearing to have more assets in terms exposed. So Lao 2019 reported that 2.4 billion people live within 100 kilometers of a shoreline, and the United Nations stated in 2017 that 600 million people live in coastal areas less than 10 meters above sea level. And the global trend of urbanization is expected to put more and more pressure on coastal resources. So it's also worth considering how that urbanization can directly and indirectly um, contribute to the destruction of mangroves and straining groundwater reserves. But of course, it's also important to consider the climate change conversation. So, the World Economic Forum in 2019 anticipate that 90% of shorelines will be adversely affected by climate change. And among the hazards posed, we're talking sea level rise and increased frequency of storm events. So, of course, there's a very real threat to life and also assets. In terms of assets, the US would cost coastal erosion at approximately $500 million per year in remedial works and loss of land. So my research used the entire coastline of County Wexford as a study area. It was seen as a suitable study area due to the soft, vulnerable coastline, which holds socio-economical significance, and as well as a large share of the population. So I was looking for an effective and timely method of recognizing areas experiencing shoreline change, which could then be used to support intervention and decision making. So previous methods of establishing change could be field surveys, and which can be time consuming, laborious, expensive, and difficult to operate at scale. And there's also a manual delineation technique where a technician might trace the shoreline from an aerial image. And this can also be time consuming and biased by the skill level of an operator. So instead, remote sensing has been applied here. Uh, Sorry, a bit of feedback there. I think someone might have. Uh, Thanks. I think that's better now. And yeah, so instead, remote sensing has been applied here to semi-automatically delineate shorelines using a sequences of geoprocessing techniques. So to get into the methodology a bit, we need a functional definition of a shoreline that can be identified through remote sensing. So shorelines are highly variable and dynamic, and we can't just use a given land-sea boundary. So due to the constant changes, winds, waves. So a shoreline indicator must be used to represent the shoreline position. Boak and Turner, 2005, present around 45 different indicators that can be used. can broadly group them into geomorphological reference lines, vegetation limits, wetting limits, tidal data, beach contours, and storm lines. And the organization and presence of these features vary on shorelines. So some popularly used shoreline proxies in remote sensing include the high water mark and mean high water and the vegetation line. So I use the vegetation line as it provides a good compromise between manifesting shoreline processes and detectability by remote sensing apparatus. So I used ArcMap 10.7 for image analysis and interpretation. And the multispectral imagery was obtained from USGS Earth Explorer, and short-term rates of change were calculated between 2016 and 2021 using images from both Sentinel-2, which has a 10-meter pixel resolution and a revisit period of 5 days, and then also Landsat 8, which has a revisit period of 16 days and a pixel resolution of 30 meters. Images from each year between 2016 and 21 were then obtained for both satellites to calculate a meaningful determination of the change. And on screen here, just a brief comparison to show the pixel resolutions with Landsat 8 on the right there with 30-meter resolution, Sentinel in the center with 10-meter, and a high-res aerial image with an accuracy of 40 centimeters. So long-term rates were calculated between 1975 and 2021 using images from Landsats 1, 5, 7, and 8. And strategy was implemented for choosing appropriate images to include, such as minimal cloud cover, and images captured between May and August were prioritized to mitigate seasonal variation in the vegetation. So the Geo Processing Tool represented here, constructed in Model Builder application in ArcMap. So the user would simply just need to input the required multispectral data files and then run this tool to produce a shoreline. So the tool works through detecting the vegetation line and producing a line feature along its seaward edge. So to do this, normalized difference vegetation index transformation was applied to the scene to enhance the vegetation identification. This NDVI image was then classified into 10 categories of distinct vegetation presence using ISO data unsupervised classification algorithm. A couple other classification algorithms were trialed, but this was found to have the best accuracy when operating at a regional scale. So from the classification, the vegetation line is then represented by the most seaward continuous line, and the image is then reclassified into vegetated and vegetated. And finally, the boundary is converted into a line feature, indicative of the shoreline position. So the tool is then run for each of the target shorelines to obtain some shorelines for comparison. So 6 shorelines were delineated for the short-term analysis, while 15 were created for the long-term analysis. So then using DSAS, the Digital Shoreline Assessment System, line transects were created perpendicular to a designated baseline. In this research, the transects are spaced at 50-meter intervals, and then DSAS produces 2 distance measurements, net shoreline change and shoreline change envelope, and 3 measurement statistics, the endpoint rate, linear regression rate, and weighted linear regression. The linear regression rate was of most interest, as this accounts for all shorelines, whereas endpoint rate would only account for the oldest and youngest. So using the interface itself is fairly straightforward, just adding your baseline and configuring some of your transects. So you might have a search difference, or you might change your search distance or transect spacing or your smoothing distance. So there was quite a lot of information gathered through the analysis. In total, we had 3,331 line transects at 50-meter spacings to calculate the short-term rates and the long-term rates. So the same set of transects were then used for all the calculations. The map on the left-hand side gives you an idea of the scale of the data gathered, and the graph here on the bottom right represents what I refer to as coastal reach 5. So this area here between Carnsore and Kilmore Quay. Here you can see the erosion rates in an area exposed to the winds, waves, and storms that emanate from the Atlantic Ocean. So this table here is the long-term rates between 1975 and 1921. And then to really oversynthesize the results, maybe you can refer to the table on the top right. The Sentinel-2 short-term calculations resulted in a mean regression rate of minus 0.81 or 18 even meters per year, and Landsat was minus 0.58. The long-term rates showed a mean LRR of 0.4, and all LRR rates are calculated to suggest that erosion is the dominant process here. So to just give you an idea of the direction I took some of the further analysis, I compared the results I got with some of the data already available. And in this case on screen here is a comparison to the results to the OPW coastal erosion lines. These OPW rates were calculated by manually delineating shorelines across four target dates. So I saw my methodology as an opportunity to update and maybe validate some of the rates already available to the public. So then there was also an emphasis put on the accuracy assessment of the Geo Processing Tool. So an error matrix was produced for each of the satellite platforms to scrutinize the accuracy of the unsupervised image classification technique within the semi-automated tool. The results showed that all platforms achieved overall accuracies which exceed the minimum threshold for image classification of 85%. And then there was also a capo coefficient calculated, which measures the likelihood of an image classification occurring at random. So all satellites achieved or all classifications achieved a value exceeding the minimum threshold of 0.7. And in addition to quantifying the error of the classification, a series of manually delineated shorelines were created using high resolution aerial images from Google Earth Pro, and then measuring the proximity to semi-automatically delineated shorelines for similar dates, taken within a week of each other. So the results of this proximity showed that the spatial resolution has a huge control on the proximity achieved by the semi-automatically delineated shorelines. So for instance, and a third satellite was actually used here, PlanetScope, which has a 3.9 meter pixel resolution and a daily revisit period. However, there's restrictions on how much data you can obtain for free under an academic license, so that's why it wasn't included in the rates, the long-term, short-term rate changes. And then, so moving on, we have the satellite with the highest spatial resolution of 3 meters has the lowest mean distance from the reference shoreline. And then that trend continues with Sentinel-2 with the next highest spatial resolution and the next highest mean distance from the shoreline. And so where we go now? And then in addition, there was a field survey at 2 sections of Wexford's shoreline to obtain the most accurate representation of shorelines possible, going out in field and taking points with the RTK GPS. So the data points are then compared to Sentinel-2 and Landsat 8 shorelines, and the Sentinel-2 shoreline achieved significantly lower distance from the sample points at the 2 sites of Ballyconnegar and Raven Forest. So just to touch on a couple of the limitations that we came across, prioritized images between the summer months, but it was also hard to do this and ensure there was minimal cloud cover. So, for instance, the 1994 image obtained was from October, and the 1999 image was acquired in November. So we were kind of forced into using some of these images because if we didn't, then there could be a gap in the data of over 10 years, which is kind of not what we were looking for. And so from the field survey as well, we realized that retreating cliff faces are also resulting in topsoil and vegetation falling forward. So if that's picked up as the vegetation line, that's another source of potential error. So that kind of just added to the quality assurance checks that we'd have to do afterwards. So in terms of future work and recommendations, I think the analysis could definitely be, you want to cross-examine with some of the other climate variables and get it dive a bit deeper into where and why um, the erosion and shoreline evolution is taking place. And we're also looking at different image classification algorithms. So we use the unsupervised image classification, which worked pretty good at scale and achieved the accuracies we were looking for. But some of the literature would suggest that more improved algorithms are available. And so looking for ways of further automating the process by maybe producing instant error reports and that kind of thing. And at the moment, this tool only works in ArcMap or ArcPro, but I'd like to look into ways of making this tool open source. And yeah, so automation is definitely huge interest. So that's it from me, and thanks for listening.